So good afternoon, everybody. Today we have with us, I think, world-renowned structural chemist, Professor Desiraju. And Professor Desiraju also happens to be our council member. I don't think Professor Desiraju needs any introduction to this audience, but just for the sake of our students and younger colleagues, I just like to mention. So Professor Desiraju did his BSc from St. Xavier's College, Mumbai in 1972 and PhD from University of Illinois at Urbana-Champaign. And then after spending a postdoctoral stint at Eastman Kodak Company in Rochester, he returned back to India and worked in University of Hyderabad for several years. And then in 2009, Professor Desiraju joined Indian Institute of Science, Bangalore. And presently he is an honorary professor in the Department of Solid State and Structural Chemistry Unit in Indian Institute of Science, Bangalore. Professor Desiraju has published more than 400 papers and has 43,000 citations, an immense number, and several recognitions, which includes Alexander von Humboldt Forschung Prize, member of the International Advisory Board of the Angewandte Chemie, one of the famous chemistry journals, and many more, right? I mean, I'm not. And of course, he has honorary doctorate from several places that includes Argentina, Kurnool, and also recipient of Acharya Pisirai Memorial Medal from University of Kolkata, and also recipient of ISA Medal from University of Bologna. Well, I think with this introduction, I will invite Professor Desiraju for his talk, Crystal Engineering, Its Potential in Modern Chemistry and Society.
Fully strapped up. You will remove that, or the names and all will be there? This is the point.
Yes, sir.
Good afternoon, everybody. Thank you so much indeed for these kind words. And I should thank your director for having invited me to give this lecture here to you this afternoon. He said that I hadn't been to cultivation for great many years, which is true. And although I visit Calcutta very, very often, so I'm glad that I have a chance to talk to all of you today. You can hear in the back. So this afternoon, what I'd like to do is, you see, first I must, there's something wrong with this mic, it's echoing too much. Is it the two mics? It's okay, I'll try. That's why I'm trying to talk a little soft, so that I find that anything that I do is triggering off something. But maybe that should be switched off. Okay, let's try again. Yeah, I think it's better now. See, at this stage in my career, you can excuse me a little bit if I am allowed to reminisce slightly. And you have lots of young people talking to you, I am sure, and coming and saying, this is my latest hot result last week. And here's the paper that got accepted yesterday, and I'm putting it up. But I can't do that because I don't have any latest hot result last week. And I don't have any paper that got accepted just yesterday. So I'm not even going to try to do something like that and pretend that I'm much younger than what I am. So you'll not hear that kind of a talk. But I thought that being especially in Calcutta and cultivation place like that, that you will appreciate if I were to give you a bit of thinking on how this crystal engineering thing developed. It's a word that is heard very often these days, and it was not so common even 10 years ago. And so first part, about 10 minutes or so, I'll talk about this. And then, since I suppose I have to say something about what my students and postdocs have done recently, about 2 minutes or so, I'll say some of that, so that at least students and all don't go back with some kind of feeling that, oh, this guy came and then he's talking all some stories. So I'll say about 2 minutes certain things that we have done, which will give you an idea about the sorts of things that are going on in crystal engineering, at least in my group. Because one of the things I've realized after being 40 years in this subject is, I don't know, maybe we can say this about all kinds of research, but crystal engineering is a very difficult subject. I don't know how else to put it. Difficult because it requires a lot of cross-thinking across various kinds of disciplines and subjects. And it involves an unusual mix of qualitative and quantitative thinking. Of course, you can say all of chemistry. That's the beauty of chemistry itself, that it is a mixture of quantitative and qualitative. But in crystal engineering especially, this is even more fascinating, even more frustrating, and very tantalizing. You don't know when to be quantitative and when to be qualitative in this subject. Because this subject is both science and art. Like all forms, like all synthesis is. Crystal engineering is a form of synthesis. So this is one of the things that at least I have found. Recently, somebody was, recently means I mean 2 years ago, because 2 years we've all been stuck wherever we are in COVID, some kind of limbo. One of the last talks I gave before the pandemic, somebody said that speaker is the person who created this word crystal engineering. It is not true. Strictly, it's not true. The word crystal engineering was used for the first time in 1955. So I was a toddler of 3 then, so I really couldn't have introduced this word. It came as a small abstract in the transactions of the American Crystallographic Association by a man called Pepinski. So he said something about crystal engineering, therefore, is a subject where you can engineer crystals or design them so that they can do what you want or something like that. But you know, we know about conference abstracts. People say a lot of things and they don't see the light of day after that. Pepinski, however, was a very good friend of another crystallographer cum chemist, a person by the name Gerhard Schmidt, who was Dorothy Hodgkin's student at Oxford, and then at her guidance and literally her order, he didn't want to go. He was sent to Israel in the Weizmann Institute to start up that place with Weizmann and others. So apparently Schmidt wanted a job only in England because he was from there. But his professor told him, you better go and start something there. And it was like a kind of a jungle. in those days. So Schmidt and Pepinski were good friends, and it's clear that they were talking about topics like this. Schmidt was a very funny guy. He started his work in 1948 with a group of students and postdocs. And he was trying this idea. He didn't call it crystal engineering. He started off by saying that there are some compounds that undergo some solid state reactions. And so he said they undergo reactions in certain ways that depends on their crystal structure. So he was trying to develop some sort of a relationship between crystal structure and solid state reactivity. And you can imagine those days, they must have been very different from today. You know, from 1948 to 1964, he was carrying out a fairly vigorous program of research in this topic. It became known as Topo Chemistry, that is chemistry of spaces. In other words, the disposition between two molecules in the crystal was deciding the nature of the reaction that those two molecules underwent. 48 to 64, he was doing a lot of work, didn't publish a single paper. You can imagine. He had brought up a lot of work, but he felt that his ideas were not yet ready to communicate. And in 1964, he and his group published, I think, must be a world record, something like 13 back-to-back papers in the Journal of the Chemical Society. This was the journal, one of the predominant ones in those days from the UK. It was called Journal of the Chemical Society before it split into Perkin 1 and Perkin 2. Most of you are too young to even know what Perkin 1 and Perkin 2 are. Even those journals, I think, have vanished today. But the parent of these two was the Journal of the Chemical Society. So Schmidt and his group wrote 13 back-to-back papers called Topo Chemistry 1, Topo Chemistry 2, Topo Chemistry 3. And so you can imagine the sort of self-control discipline he had before he felt the whole idea was ready to present. The far cry from the way people do research today, just doing anything, cut, do something, put some communication, I got some chemtron, I got this, I got that. You know, it's like a Maggi noodle sort of thing. Whereas you want to make some slow biryani or something and eat, you know, you will wait slowly and you will do the things. You will not, you know, do all this. That quick research will come quick, but it also goes away very quick also. Shelf life will be in matter of minutes. And then they'll go on to something else. Then they'll say, a graphical abstract kaisa hai? Very colorful picture we'll put. Something, internet, visual media, so many things they say. You know, I always say that when you take these color pictures and all, is the chemical message communicated with a black and white picture? Because if it is, then that color picture is simply an unnecessary distraction and a stupid distraction at that. So be careful when you're doing work and all. You be careful what you're doing. You must exercise some caution and restraint. Look at this guy. He just started his career. He was a young man. You know, he died tragically at the age of 51. And I found out much later, his famous student, Professor Lahab, told me that Schmidt and I shared the same birthday. So unfortunately, I never met Schmidt because I started my career as a PhD student in 72, which was the year after Schmidt died. But in the short career, 94 years, 94 papers, he developed, I think, and even he didn't use the word crystal engineering, by the way. He, after writing these papers, he wrote a small review in Pure and Applied Chemistry. And he said that this subject is coming slowly. He said some first stages are happening with my 13 papers where we looked at some crystal structures and we looked at some reactions and some correlations between molecular and crystal structure. He said a third stage will come, which we can call the stage of crystal engineering, where we will get a more predictive control on how to design crystal structures themselves. That's all that he said. So this was the state of play at that time. When I got into thinking about all these things in 1979, when I joined the University of Hyderabad. And, you know, I would like to say that, you know, when you express something, when you want to express a scientific idea, all of us have felt this. Our scriptures also say that there are 4 voices. I think we know, those of us who are familiar with the scriptures know that they say there are 4 voices. The voice that feels, para. The voice that sees, you know, pashyanti. Then the voice that is able to sort of slowly conceptualize something, that is called madhyama. And finally, the final voice, where you exteriorize, like what I'm doing now in a speech. The 4th voice, the final one, is called Vaikari. So when I first started all this thinking about this, that para, when you feel something, you know, you feel something is wrong. You're looking at Schmidt's work and all that is not enough. Something is there, but some sensation that some big things are missing, you know, that is sort of a feeling that all scientists get, you know. You don't start a research area just because your postdoc supervisor was doing that area. They're all rubbish research. Because you will be missing the only thing that is important in research, and that is novelty. You feel something is wrong. And second one, pashyanti, you see something. You see some funny observation, either a chemical observation or a crystallographic observation, something that is looking odd and it's looking strange also. So you're actually able to see something, it's going beyond feeling. Eh? Then this madhyama, what you do is you try to express it in some initial papers and all you start writing. They'll all be all crazy papers, all wrong things and all will be there in those papers. One should not worry. Later on, you know, you see, I look at some of my papers of those days. So how did I write all this rot? You know, really. But then at that time, you know, it was what you were trying to conceptualize the whole idea. Finally, you get into the stage of Vaikari. That is, you are able to then tell, okay, now this is what it is. And I think that's what happened to me over 10 years in Hyderabad, first 10 years. And I wrote a book in 1989 that is fully, 89 means 71 he died. So about 18 years after Schmidt died, when we could write a book called Crystal Engineering. And this book really sort of, I have to say it, I mean, I cannot be unnecessarily immodest. It made me a known name. Because this thing, crystal engineering, which was maybe perceived by Pepinski, felt by Schmidt, something I was able to exteriorize it. So I got this crystal engineering. And I took a bold step and said it has nothing to do with solid state reactions and topo chemistry and all that. But it's a more general subject that concerns how molecules get together, the interactions, the kind of things that geometries, orientations, what makes a crystal structure what it is. And then I said that is crystal engineering. And this was a definition that was picked up widely by many people all over the world. And I would say it still largely stands the test of time because, you know, something I wrote here, the understanding of intermolecular interactions in the context of crystal packing and the utilization of such understanding in the design of new solids, blah, blah, blah. Now, the other day, once again, I was just last month or so, I forget when I was reading this book. And then I felt, okay, I felt a bit happy because I said they have not said too many wrong things in this book. Actually, I couldn't find anything that was blatantly wrong, even after 30 years. And I believe many people have felt that this book really made them change their research area and try to get more into crystal engineering. This was the book that sort of turned the corner. And it's very strange in chemistry because I was once talking to some famous people. They said big ideas in chemistry usually come from papers, they don't come from books. A book is not a standard way of expressing oneself in chemistry. But then in many ways, I'm quite a strange person, as you might have made out already, because I don't think you've heard too many talks, this sort of stuff that I'm dishing out to you. So it is, okay, chalo, book got written, people started accepting. Today it looks like textbook material. And in fact, I too felt that after some time, because 20 years after the book, I got together with two younger colleagues, Ramanan in IIT Delhi and Vital in NUS, Singapore. And we wrote a textbook on this area. And Ramanan made a very valuable contribution, which was not there in the 89 book, regarding crystal growth, because that was his specialization. Because by then, the growth of crystal itself became important in the design of a crystal. That's the connection that came in. And Vital, of course, is a world-renowned expert in this type of compound, which all of you know today, the metal organic frameworks or MOFs. So I'll talk a little bit about that in the next part of the talk. And so we wrote this textbook in 2011. So sort of now it is there. It's a big subject on its own. And moving on, the big question therefore is, to simplify, and why I said it's a difficult subject. Given the molecular structure of an organic compound, what is its crystal structure? Schmidt was asking that, he was expressing it in a different way. He said there's some connection between these two. But now can we make a more specific way? I've given you a molecule. I'll give you a molecule because molecules can be made in the lab. So we start with the molecule. Can you tell me how the crystal structure will be? Okay. It's a very difficult question to answer because look at this. Then the second one comes in, and this is connected with hydrogen bonds, we know. And this is how it looks in the solid state, benzoic acid. Now, look at this. And then the next one comes in. And then the next one, well, you got some hydrogen bonds. Then the next one comes in. So you see how acetic acid crystallizes is different from the way in which benzoic acid crystallizes. So which means that this crystallization, the crystal structure doesn't depend all acids therefore don't crystallize the same way. So there's something else going on. So the simple functional group approach, which is used in molecular organic chemistry, cannot be used in crystal engineering. So that means everything is influencing everything kind of thing. So this takes you into the realm of complex systems, supramolecular chemistry, etc., which was becoming very big after 89, after my book was written. Because Lane and that gang got the Nobel Prize in 87. So supramolecular thinking was just sort of beginning. In the 1990s, there was considerable amount of development in trying to bring supramolecular ideas into crystal engineering. So we're going towards greater complexity. So then the main problem is behavior of a molecule depends on the nature and positioning of all functional groups in the molecule. And please remember here, the hydrocarbon part also constitutes a functional group, because hydrocarbon residues interact with each other, ring or chain or whatever it is, hydrophobic. So crystal structures are therefore not related to molecular structures in simple ways. They are emergent properties. They are not easily predicted. Now tell me what you see here quickly. Bird and panther or face? How many saw bird and panther first? How many saw face first? Even I saw face first. But if you look little carefully, you will see. So that means the whole is more than the sum of the parts. This is the problem in crystal engineering. You can design functional groups and all as well as you want, but finally when you put them together, something else happens. So this is called emergence, this is called complexity. And this is why I said it is a difficult subject. It's not an easy subject. So unless you're a bit, weird person, you don't want to come into this subject so easily. But it's very useful, as I'm now going to show you, which means more people have to get into this. Now, we leave this. Because of this problem, a simplification is needed. We can't make each crystal structure a different story. Then we'll get like Mahabharata. It will become very big. Because there won't be any rules and things how to develop it. So, in 1995, I wrote this article in Angevante and defined the term supramolecular synthon with analogy to Corey's molecular synthon in synthesis. I already told you, crystal engineering is a form of synthesis. So I said these like this benzoic acid dimer, acetic acid catamer, those patterns of interactions define what is called a synthon. And suppose I say to a first approximation, a particular synthon is characteristic of a particular combination of functional groups. At least I am getting an approximate idea about what happens when you go from molecules to crystals. Synthon is only a practical approach to what is otherwise a very difficult problem to solve. And like the crystal engineering name also, the synthon name was readily accepted by people in the subject almost as soon as the article was written, which is why this article is still quoted, I don't know, some 300, 400 times every year. It goes on getting citations after so many years. Now, so what are some of these interactions? Here and all, I won't bore you with the details because I want to come to the modern day examples and future trends. Hydrogen bonds, halogen bond, etc., etc. These are all things that we have studied threadbare. And these are all the weak interactions that hold molecules together. So, if you take a particular, any synthesis, if you take, it has got a combination of strategy and methodology. And strategy and methodology ideally should be separate from each other. They should not sort of start mixing with each other too much. Little bit you can mix. Sometimes it is strategic to mix strategy and methodology, but usually you keep them separate. Strategy is the plan. Methodology is how you put it together. So interactions correspond to the methodology of crystal engineering. These are the things you actually use to put the molecules together. The strategy is the grand plan with the synthon. And I say that if I have a certain combination of synthon, let me try to get that. Now, okay. Now we come to the first of the examples. You take crystallization itself. People have been taking salt from the sea, for millennia. Crystallization is a purifying technique. You take a big lump, some impure things, you crystallize, and then you get the pure stuff. So the single problem I'm going to tell you that we have done some work in the last 10 years, so that I don't tell you about some ancient stuff. How to get more than one molecule in the same crystal? Because you are going against nature. Crystallization is an excluding phenomenon. I want to get more than one molecule coming into a crystal. 2 is well known. You can put 2 quite easily. Wohler did that first in 1840 with quinhydrone. You could put quinone and hydroquinone together and get that molecular complex. Can you put more than 2 in a complex? So we developed this particular technique. And so we said with some difficulty, it is possible to put not 2, but 3. Not 3, but 4. Not 4, but even 5 and 6 also under certain conditions. So this becomes very, very tricky because this is not easy to do at all. These experiments on higher core crystals, as we call them, They are so difficult, like some of the synthetic experiments, that the same experiment will work in one person's hands and it will not work in another person's hands. Because I have seen this in my own group, when certain students were considered to have green fingers, so the others will go to him or her and say, please, you do this experiment, because if I do it, it won't work. Okay, so there is still a lot of, this is why chemistry is such a nice subject. Everything is cut, easy, means then what is there? It's like becomes like an MSc project. Research to be research means you've got to have some difficulty should be there in the subject. Actually getting 4 like this is very, very difficult. In the whole world, only our group has managed to get 4. Many people have got 3. Right now, I'm sitting on a group of 60 ternary co-crystals, 3. I'm trying to publish it all together in one paper. So 3, I think many people are getting, but 4 they're not getting. So this is the only part of my individual research I want to talk about. Now we'll come to the challenges. Now, I wrote this review paper with Professor Nangi a few years ago in Angevante, where we defined 5 places where crystal engineering is taking us tomorrow. So from now on, for the rest of the talk, it is now only projections into the future. We're done with how this crystal engineering came, little bit what we did. First area is pharmaceutical co-crystals, the one on the top, 12 o'clock position. Okay, then the next one is, I think, this mechania, the solid state reactions. Then we come to thermosalient materials, actuators, mechanical properties, small crystals that go on bending, turning, twisting, etc., etc. Fourth is this giant topic of metal organic framework, MOFs, and their cousins, the COFs, covalent organic frameworks. And the fifth and last is this solar energy, photovoltaics, and renewable energy sources. So these are 5 big areas of chemistry / application / industry where crystal engineering can take you tomorrow, and which is already happening today. So this is not completely speculative and in the future, but it is already happening today. Now, quickly, I want to maybe maximum less than 3 minutes each area to give you just a glimpse and a flavor for what's happening. So these are the pharmaceuticals today, 80–90% of the pharma is using the solid drugs, whether it is ointments or tablets or lotions, powders, capsules. Only 10–15% is in the injectable form. So usually when we say drug, we are talking about solid forms. Solid forms can exist in different kinds of ways. The same chemical entity can exist in different crystal structures, which are called polymorphs, hydrates, the name is obvious, solvates, salts, eutectics, and finally the part where we are interested, co-crystals. So when I said we are trying to put more than one molecule together, why do you want to do that? Because we get these co-crystals which are called pharmaceutical co-crystals. And why do we want them? In 2018, FDA came up with an important classification. You can't read this green stuff. So let me read it for you. Pharmaceutical co-crystals have opened up opportunities for engineering. See that engineering word. Solid state forms beyond conventional solid state forms of an active pharmaceutical ingredient such as salts and polymorphs. Now see these polymorphs like diamond and graphite and stuff like that. So if you have 2 polymorphs of a drug, one can be very soluble, one cannot be so soluble. When you try to make one into a tablet, it will compact nicely. The other one will become a paste. So it's very important that you know what polymorphs we are getting. China has made a fine art of selling India junk polymorphs today. They make the thing and the good polymorph is sent to America, the bad one is sent to India. It's going on all the time. So it's all real practical problems. It's not some theoretical, some jacks and Angevante. No, not like that. This is the real world I'm talking now. This is what they're doing. So it's important that you get the correct solid form. What is the relevance of co-crystal in a scenario like this? See, we wrote a paper on this a few years ago in a journal called Molecular Pharmaceutics. There is a strong medical background that an antibacterial and an antimicrobial have to be given together for various kinds of infections. So here we have norfloxacin NF, which is an antibacterial, and then you've got sulfathiazole, which is an antimicrobial. Now these two are actually told as a physical mixture or given as two different tablets by doctors. Now we found that these two form a co-crystal, like two things in the same crystal. The problem with norfloxacin is it is very insoluble. Sulfathiazole, on the other hand, is soluble. So when you have a physical mixture of the two, this is the situation here. The norfloxacin is solvated by water. The sulfathiazole is solvated in water. And going through a membrane, why membrane, I'll tell you. The norfloxacin is not let through, sulfathiazole goes through. Now, this results in, there are two issues here which need to be explained. A drug, when it is taken in a solid form, it has to be bioavailable in the active site, which is deep inside the cell, cellular mechanism. So first things first, the drug has to be soluble. Second, it has to be permeable. That means it has to go through the intestinal barrier. That is the aqueous lipid barrier it has to go through. So drugs have to be both soluble and permeable. When you make a co-crystal, the beauty of the thing is, this has been found only recently in the last 10 years, that it significantly can and advantageously change both the solubility and the permeability characteristics of a drug. So you can take, in this case, norfloxacin is not soluble. Sulfathiazole is soluble. When you take the co-crystal, on the other hand, you see, it is already there like that. So there is an extended thing. What does it look like? It looks like a synthon again. So this is what we call an extended synthon in solution. So that there is some still loose association between norfloxacin and sulfathiazole. So much so that it increases the solubility first. And second, sulfathiazole literally drags the norfloxacin through the membrane. So it improves both solubility and permeability. Now this is very big and it's very important. And this is why so many people are doing so much work today on pharmaceutical co-crystals. Now, see, it's really nice to see, when you have the advantage of reminiscing, and I said at my age, from 95 to 2000, that is how much, okay? 15 years, 25 years. We moved from supramolecular synthon. The second picture, that black one, is what is called the synthon in a pharmaceutical co-crystal developed by Mike Zawarotko, who is now in Ireland. In those years, he was in Canada. And the third one, middle picture, is when these co-crystals could be formulated. Remember that you make the drug and you must formulate it in the form of tablets, capsules, and this and that. India is the world expert of formulation. We cannot make drugs cheaply, but we can formulate them very well. The fourth picture, there, these are all cover pages of prominent journals. The fourth picture represents a special issue where they were talking about different polymorphs and co-crystals having different compacting properties and tabletability properties. And the fifth and last in ChemCom has to do with 5 co-crystals that are now currently in the market. So from idea to market, it has taken only 25 years, which is a very, very short time in chemistry. Usually you have to wait for a great deal of time, which means that these old ideas of the synthon and all those things, original crystal engineering, you can come to a marketable drug today. And this is big. And this is why, again, many people are working on this. So this is the first of the 5 areas. Now we'll leave this. Solid state reactions. For a long time, you know, Schmidt was some of the early fellows. They found that you can do solid state reactions with grinding. Very important in industry because you can do green chemistry, you don't use solvents. And just to give you an idea, some 3 famous names I have put. Professor Boldyrev in Russia, Professor Rastogi in Gorakhpur University in India, and Professor Toda in Japan. All people from the earlier generation. I was fortunate enough, blessed enough to know all these 3 people personally. And I have seen the Rastogi's paper in JPC of 1962 or 63 is still cited today. So many people have written so many papers in JPC. This paper continues to get cited all the time. He showed that if you grind the 2 things, organic things, you can get donor acceptor complex in the solid state. And beautiful paper. Toda also. Toda has taken all reactions like Reformetsky and Bayer-Villiger addition and all that and shown that it can be done with in the solid state. Sebak, when he wrote his famous review on organic synthesis in 80 or 81, he refers a whole 1 page to Toda's work in this business. So it's important industrially. You know, there's big money involved in all this. That's another thing. You please remember, students especially, even faculty. You will have to go to industry for money. Abhi sarkar ke paas paisa nahi. I'm telling you, don't go on sending applications to SERP and DST. Wapas hi aayenge. And even the era of godfathers is over. No, his supervisor knows somebody in the they want nothing, all over, zero. You'll have to go to private fellows to get money. Tomorrow, students, don't start dreaming about faculty positions in academic institutions. Oh, bekar hoega by the time you become all PhD postdoc. All my students, I'm telling them, join industry straight away after PhD. They're all joining. One of them has become vice president also of my lab. In just about 15, 17 years. So please think about it. Huh? This माँ बाप कल्चर या सरकारी समथिंग सरकारी नौकर पेंशन मिलेगा from cradle to smashan government will take you. I'm telling you really. No, I'm not bluffing. Why should I bluff here? No need for me to bluff. What am I getting out of it? But I'm just telling you, don't have some preconceived notion. My advisor, I've seen this in some TIFR. TIFR में तो और अलग बात है. He gets PhD in TIFR. He wants faculty position only in TIFR. He doesn't even want in TIFR Hyderabad. He wants in TIFR Kolab. हाँ. क्या ऐसा attitude रखकर कहाँ जाएंगे तुम? Whole world is moving and then you are stuck in some whole world of some TIFR, Homi Baba, CV Raman, all sorts of things, all old junk. I know he did his work in cultivation, but if you mention his name to him today, he'll give you one kick in the pants and say, what are you doing? You don't tell me what I did. What are you doing in cultivation today? The other day I read one paper. Some of you know, you follow me on social media. I'm doing a lot of research into the Sterlite company in Tamil Nadu. I don't know if you know that. How they stopped the copper production in India. We used 40% of our copper was coming from there. And then all these fellows, Break India forces, they stopped that plant and then they're jumping in. Some Chandrachud is stopping it in the Supreme Court. So in connection with that, I read an article on copper in ancient Indian metallurgy. This paper which I read, I'm telling you, cultivation and one man called Panchanan Niyogi. You go and check it out. It's there in your library. It's part of an IACS publication. IACS apparently had a series of monographs and volumes that they used to print out in their own printing press. And this Niyogi's paper, I have read it many times. Wealth of information that tells you that our fellows knew a lot about copper smelting and all that. Okay. So this is the kind of thing that after 110 years, somebody is sitting and reading your paper. Any of the papers that we are writing today, somebody will come and read after 110 years. It happened in your own institution. I'm not telling about some different things. So suppose tomorrow your director says, come, I'll give you a fellowship to just go through my library and see old manuscripts for 2 months. I'll happily come. I'm sure there are lots of things there to find. What happened? What happened to us that we were able to do this kind of quality? That I'm not some foolish person as far as chemistry is concerned. I will not waste my time reading Panchanan Yoga. Is an incidentally interesting thing about that article, which will also tell us about our own institutions. This gentleman was in the University of Rajshahi. And he apparently used to come and go from cultivation. And then say, I want to read this book, that book, and all that. The cultivation faculty were telling him, no, you can't enter this place. You are from some Rajshahi, we are Calcutta. Something. He writes all that in his preface. How do I know all this? He said it's printed by them, but they never cooperated with me at all. He's written all this. Jaakar dekho. So we were capable of all these things here. So what are we doing today? Please think about it. I think I better stop now because otherwise I'll go on and on. Mechanochemistry, so chodo. This is plastic deformation. This Malla Reddy must be listening somewhere in ISER. So he is the one as a PhD student who started this kind of work in my lab. He was a very good student. Now become some famous professor or something. He found some crystals that were just trying to put them on the diffractometer. They were just bending when he tried to mount them also. Now, this is not very usual in a crystal. Any student, average student would have forgotten it and tried to look for a good crystal and then mounted and then said, sir, I got the result. This man became curious. And that's another thing about being nice in science. You don't have to have many things. You have to have only two things. Courage and curiosity. Bas. All other things you can learn from books. These two things only God can give you. You can't learn courage from a book. You can't learn curiosity from a book. So this guy was curious. So he started poking these crystals around. And then we found some systematic trends in this. And one thing led to the other. And we did a whole lot of work on this business of mechanically deformable crystals, crystals that are plastic, crystals that are elastic. Plastic means when you deform, it doesn't go back to the old shape. Elastic means if you deform, it will go back to the old shape. Then there is something called super elastic, which is actually a kind of plastic. Like all nomenclature in chemistry, this one is also confusing. So super elastic actually is a kind of plastic. And so many good students I've had, very curious and intelligent people, very brave students who took up research in this area. So then after some time, we had some fun. So wanted to have some fun. As I said, when you go on in research for some time, you're always looking for new things to do. So I think about a few years ago, this top article here, this CM Reddy, that is Malla, and S. Saha, Shubhankar Saha, and MK Mishra, Manish Mishra. There were 3 students in 3 different phases of this mechanical work. So Malla finished in 2005, I think. Manish finished around 2012-13, and Shubhankar finished in 17-18. All of them are happy. These fellows all got academic jobs, but we decided to write an article where myself with these 3 chaps, so that to show also like how we are doing all these things over a period of time. And appears that this article also was well timed, because after we wrote this article, we had so many other articles coming. I'm sorry you can't read the script there. All our review articles in the last few years written by international experts. I mean, these are not the fellows who wrote these other articles are not exactly novices. This is Naumov, Professor Naumov from New York University, Abu Dhabi, who's a very big figure. Calvin Sun in Minnesota. R. Chandrasekhar in Hyderabad University. Tomislav Frisic in McGill. And then Malla again on his own, he wrote in ChemSoc reviews. Chris Bardeen, and I was so happy to see Saumyajit Ghosh and Manish Mishra, both who worked with me, writing an independent article. Both are in academic positions now in the private industry. This is another place where you all can look, instead of looking for the Sarkari Naukars, which will never materialize. There are many good private universities in India today. And recently I had my own personal experience. One of these private universities asked me to recommend some names. And I looked at things and sent some PDFs actually in WhatsApp. Not even, the people didn't even know that I was sending their PDFs. And they called them for an interview, each of them, in about 2 weeks. At the end of the interview, they promptly offered them a job and they both accepted, and within 1 month from start to finish, both are working in that university. Now you try to get that kind of speed in a government institution. Many years lagega. This saying you have to have so many years of experience, postdoc. You must have 5 letters. You have to work only with Nobel laureates. It has to be only in America, not in Japan. All these things they will start asking. Then baad mein to they'll say some rule has changed. Then they'll declare you are not eligible. Screening committee, second screening committee, selection committee. Some old wise men will come from all over the country and say, "Ha, acha hai, acha nahi hai," and all they will start talking. And then suddenly they will give one job somewhere. Somebody else will not get a job. Private universities are not doing this. There are half a dozen of them today in India that are quite good. Let me tell you that. What is happening in government institutions is one junk kind of teacher is attracting some junk kind of student. Double junk ho raha hai. So just think, you have to think. You can't just go on assuming that what worked in the past will work in the present and future. It won't. This whole country is hell. It's changing so fast. If you just get stuck up in some old world, something 1757 Plassey, 1857 first war of independence, 1911 capital got shifted from Calcutta to Delhi, then partition, Bangladesh. Forget all that. Ho gaya. Whole world doesn't begin and end in Plassey. Please get a control on yourselves. I'm so fond of Bengal and Calcutta. That's why I feel free to talk to you guys like this. Many times I don't feel like an outsider in this place, because some of you know that my family has a very old connection with this city. But that apart, you fellows have to be realistic and modern, So all these people wrote review articles. I feel very happy that something which, see, that's another thing in science. Whatever you do has to be useful at that time. As I always say, it is better to be approximately right at the right time instead of being fully right at the wrong time. Remember that fully right and all, we can never do that. What is fully right? The timing has to be right. Something has to. Even Schmidt, I think he waited for so many years to write those back to back, because perhaps he knew that in the 1950s that community won't accept what he's doing. I haven't talked to you at all about weak hydrogen bonding, which is another area where I've become relatively well known. I can tell you many papers of mine in the weak hydrogen bonding area, I delayed submission because I felt that this audience is not going to understand it also. Keep it in reserve. You should always behave like, I have 1,000 rupees and I'm not going to show you, but I will only spend 100. You will only see 100 rupees. I will not show you the other thing. Today, all the young scientists and all, they have 100 rupees and they want to go and spend 1,000. Telling you, I see it all the time. But how will it look? It will look all like that only. It will look. Chalo, these are all more things. This Shubhankar did all this stuff. MOFs. this Yagi, Robson. They started this whole thing. You know, the time when I started Synthon, Richard Robson in Australia developed a similar theory for coordination compounds. And Yagi gave it that fantastic name, metal organic frameworks. So that then you started developing this whole sense of framework structures which can store gases used for catalysis, separations, huge amount of papers, inorganic side. And the principles of designing a MOF are the same as part of crystal engineering. So today, many journals of crystal engineering will write half the papers on organics, half the papers on MOFs. MOFs and their cousin brother COF both come fair and square in the domain of crystal engineering today. But then there's a big problem, elephant in the room. After so many papers on MOFs for 20 years, we still don't have a big use for them. The compounds to beat as far as catalysis is concerned are zeolites. The problem with MOFs is they're acid sensitive, they're moisture sensitive, they're sensitive to a whole lot of things. The only thing about them that's good is they crystallize easily. So when you crystallize easily means you get crystal structure easily. Crystal structure easily means you get a lot of papers. And citations jara bad jayega, their impact factor, which something will go okay, but you're not going anywhere. And here I have to read some of the things, you know, about this carbon dioxide capture. Current global carbon dioxide emissions are so much, increasing 10% annually. MOFs will capture CO2, but the molecular weight of a MOF is about 10 times that of CO2. So you need a lot of MOF. Actually, CO2 released from industrial chimneys also have oxides of sulfur, nitrogen, moisture, carbon. All these things will decompose MOFs. They are not even temperature sensitive. And still the classical method of CO2 removal by amine scrubbing is much cheaper than doing all these MOFs things. Similarly, Yagi talks about using MOFs to capture water from the desert. This may be okay in a desert climate. And he actually makes one nice movie where he shows in the desert, this MOF is there, he puts one tap and water comes out. And looks like magic. But see, this is not our problem. In India, our problem is too much water and not enough water in the right places at the right time. So anybody who's trying to sell MOFs in India saying you'll get water from a desert, the sales will be zero. These are all the traditional ways of saving water in India, which we've been using from time immemorial. You know, I'm actually standing near one of these places, which is, and this is common in all parts of India. And this place is located exactly here. And so this is me, and then this is this Cheruvu. So you take our 100 rupee note. This is this Vav, which is this Gujarat well, which is a traditional way of preserving water in a desert area. So you don't need Yagi to come and tell us how to get water in a desert. We already know all this. So when you choose an area of research and try to start writing papers, okay, you went for postdoc to one of those labs that is getting water from a desert using MOFs. Then you come back, the same cadmium, whatever you use, I want to use cadmium also. If that fellow uses zirconium, you will also use zirconium, because that's what you saw in your postdoc lab. Do you need that kind of junk in India? We don't. You find me a way of storing the water and preserving it and keeping it properly. Now that will earn you some brownie points. So the area of research also must have a close connection with what are the needs of your local environment. Okay, please be careful when you planning a research area, want to get into something. This must be part of your big plan right from the beginning. You can't, as I tell a lot of people, especially in the MOF area, don't produce the compound and then say, I'll find a use for it. First, think about the use. Then try to think what kind of compound do I need to make to satisfy that use. Chemistry is always a practical subject. It is not some theoretical stuff. Big discoveries in chemistry have always come from practical things. Louis Pasteur's stereochemistry. He never went there thinking I'm going to get D and L and all that. There was a problem in the wine industry. Wine was going sour. The wine industry was in a panic in France. They called him as a consultant. Then he found these crystals of this hemihedral tartrate in that rest is history. Bayer process, nitrogen fixation. How did it start? They never just said, okay, Haber, come and give us this iron catalyst. World War I method that Germany's supply of potassium nitrate got cut off by the Allies. So they needed this nitrates very quickly. So BASF company called this fellow Haber. So he then played with one tin can, literally. I've seen that tin can in Ludwigshafen. Those of you who've been to that lab will. The tin can, he punched some holes in it or something. That was the first nitrogen fixation experiment. There's a real practical, immediate, pressing need for something. Big results have come in chemistry always from stuff like this. People never went into some nice 5-star lab and said, okay, today I'm going to do something and then that will give me a Nobel Prize. No, nothing like that ever happened. So disabuse yourself of all those ideas. Anyway, to go on covalent, this Rahul is doing all these things in ISER. So they have got the advantage over MOFs that they don't need these heavy metals. They are also completely organic. So they can be used for a lot of interesting things like drug delivery and dietary things and things like that. But this article that he and his students wrote in JACS, really very realistic article. Scalability, stability, processability of these COFs is still far from resolved. And nobody knows these issues better than Rahul, who is one of the leading figures in this COFs area in the world today, I can tell you that. And big problems, but see, you have to take big problems only, difficult problems. Why take easy stuff? You know, I'll tell you in chemistry research and all, better to take a difficult problem and fail than to get an easy problem and succeed. That failure will take you to some very nice places after some time. These are all the COF papers written in just 4 years, you know, this application. Finally, solar energy, functional materials. There's not much to say, except that by 2030, solar energy is going to become so common in India. Already in India and Tamil Nadu and places like that, it's very common. Electricity will be practically free in India by 2030. And much of this revolution will come from wind and solar. So you've got silicon, which has got some disadvantages. Now you've got perovskites. And then where crystal engineering comes in is with these organic things that can be used for solar energy conversion. So these are these polythiophenes and stuff like that. So this is, you know, again, it comes back to the age-old problem that when you take an aromatic molecule and the aromatic molecule can stack like this or it can pack like this. These are the two classical shapes for organic molecules, aromatic things to pack in crystals. And a very famous, now famous paper that I wrote with Angelo Gavazzotti in '89, actually 3 papers, 2 in Acta Crist and 1 in ChemCom, and where we talked about these 3 forms of association of aromatic rings. So this comes back again back to polythiophene, because whether it stacks plane to plane or plane to edge, the energy conversion properties are quite different. This is what they found recently. And finally, I'll say that these fields are all very fast growing. Like science today is such that, I mean, I can call this my area or something where I've done a lot of things. Today, some of the papers in crystal engineering that are coming, I don't even understand the titles. And this is quite natural. You know, I remember again, I'm thinking about cultivation and I'm thinking about some of the old figures here. I don't know how many of you even know Professor Ghatak or remember him. But Ghatak was synthetic organic chemist, and apparently he reviewed my first project that I sent to DST, some stupid thing. And he think, okay, Hyderabad New University, something he has said. And he told me this many years later, actually. Apparently, he'd been to Germany. And he was a good friend of Professor Vogel. from Cologne, the person who did this famous anthracene work and all that. So apparently he was sitting with Vogel in the evening after his talk and dinner and all that. And then he was complaining. He said, no, the whole research, chemistry research in India is all junk. That's what Gatak was telling Vogel. He says, we are all doing something, but it is nothing. So then I believe Vogel said, he just smiled, I believe. And then he said, he pulled something from out of the drawer. And then he said, how do you explain this? And then he showed him my first paper in accounts of chemical research in 86, where I told that middle voice, that Madhyama, where I was thinking some ideas before this crystal engineering word came into my head. And I believe he said, what do you make of this paper then? If it is the chemistry research in your country is so bad. So then Ghatak said, I know this fellow. His DSP proposal, he suddenly remembered. And ever since after that, this gentleman developed a great affection for me. And he always used to, even after he moved to IACB, I went to see him over there in his last years, and then he was telling me so many sarcastic things. And he actually told me, since the poor man is dead and gone, such a famous chemist, he told me, he said, Gautam, he said, same thing that I'm saying to you today, He said, I used to think JOC is my own journal, my family journal. He says, today I can't understand the titles of the papers in JOC. He said this to me about 20 years ago. I'm telling you the same thing now. This is the nature of science. It goes on moving like that. So fast that you can't keep up with it. And this is written by that fellow Naumov, Look, I can't understand this. I didn't even know there's a journal called Small Structures. Perovskite solar cells have attracted. He's taking perovskites and putting organic thing on top of it. Ionic liquids he's putting. You would not think that you could put these two things together and still within the rubric of crystal engineering. So, you see, this whole thing is moving fast and furious. And you fellows should be part of this fast moving thing. Otherwise, you will get sort of left behind somewhere. And so we've come to the end of the talk. This is, you can't see it from such a distance, but this is Naumov and me in Japan when we were both much younger. And he was still a postdoc there. This is Mike Zavarotko of the Pharmaceutical Crystals. He took up from my Synthon 95 work, and then he made it into Pharmaceutical Crystals. And this is a funny picture. This is me and Yagi. We met in some strange place by coincidence. Neither of us knew the other was there. So he insisted on taking a photo together. And this whole MOFs thing. This is an old one. This is Whitesides and Diedrich, who unfortunately passed away last year. Not so old. And we were all in some IUPAC meeting. This is, of course, me and Professor Nangia in the Gordon conference. These people I haven't mentioned. Roland Burzy. Could mention so many people. I just picked up these pictures at random. We did that famous work on aspirin polymorphs together. And these are some of the students, recent times. Malla, this is this Ram Jetty, who is vice president of Mylan today. Private company, 16, 17 years from PhD student, he has become vice president. Of a big multinational. This is Professor Birada from IIT Kharagpur. These are all other students whom I mentioned today in the course of the talk. And have worked for 40 years. I said I didn't see Schmidt, but I saw Lahav, Lazarowitz, who are still happily with us. Both got the Wolf Prize last year. And they were Schmidt students, and so they were very happy. Schmidt had his 100th birth anniversary. Both of them, that's why they told me that you share the same birthday with him. You have to come for that conference in Weizmann Institute. So there was a lovely symposium celebrating Schmidt's 100 years. And so we all met. That was the last conference before COVID that I attended, as I told you. So many people, so many memories, so many different kinds of incidents. This is the great thing about doing higher level science. At this international level now, when you see all these people, you realize we are all the same, in the end. We may be living in Calcutta or some Bombay or Zurich or, Seattle, whatever it is. But finally, this searching for the unknown, the same beautiful thing, this sort of a thing is what keeps people together. And I think this is what really sort of has kept me still, happy and enthusiastic, so that even when I'm not doing active research anymore, really I'm not. We're doing a few small things, but the chance to talk to younger people, to tell people what is happening. You fellows are very, very lucky. You are living in a country that is at the cusp of change, which is changing very much for the better. So please take advantage of this and take advantage out of the disadvantage. You are not getting that sarkari money, but that sarkari money is a cursed money because it just inhibits you and makes you think small. Like we had no money in Hyderabad, nothing was there, it's jungle. Then later on, Lahav told me that Weizmann Institute was a jungle like that. All thorns and scrubs and snakes, scorpions. Hyderabad, I see it. We never had a phone in that building for 10 years. Today, we can't do without a cell phone for 2 minutes. 2 seconds also, we can't do without a cell phone. 10 years, there was no phone there. Some sheds. Something. My very first experiment on solid state Topo Chemistry, my student, Dr. Sharma, we put something in a petri dish outside. And then I said, after some time, to go and see what's happening. He came back and said, sir, you better come. Some cow is there or something. I said, what is happening? So we went outside. The cow is nicely licking that petri dish and eating up all the cinnamic acid. Yeah, it happened to me. Really, it happened. So you talk about all these things today, people fighting about cows and whether to eat them or not and whether to worship them or not. I saw cow really eating up my experiment. So yeah, I have seen so much that none of the stories that you people tell me, I don't believe all these things, because see, half the fun is enjoying that, the whole thing. You should not take it all in a bad spirit. Once you want to go somewhere and do something, something is bugging you, that first one, that para, that first voice that tells you something is wrong. That is the most important voice. The 4 voices, that is the most important. Because once you start getting bugged by that, then you won't really leave the thing until you find that there's a logical conclusion to the whole thing. So I'm actually very happy, very grateful that that I've lived long enough to see this subject like this, so that it has gone into some fantastic places where many of the fellows who were with me from the beginning, Professor Braga, I didn't mention at all, another wonderful friend, Braga and Severotko, came onto this crystal engineering idea right in the beginning. And there were cluster chemists who quickly switched over to this. They said, switching an area is important, When you see something is nice, when there's a fast moving train, you should not be scared to throw the old and keep jumping. And that's what some of these people did in the 90s. So they tell me, they said, we never knew it's going to happen like this today. And the unpredictability of something is also its beauty. If you knew everything, as I said, it will be an MSc project. It won't be research. It won't be fun. It will not be, worth it. Then I can go and do something, get into IAS or something. Many, many things you can do. Why are we doing this? Because we're all slightly different. So make that difference count, okay? Young faculty, students, make that difference count. Don't just let go and say, something. That Babugiri, IAS, secretary, PSA, they will do all that stuff only. That's all they're fit to do. Leave all that. Chodo. Do your work properly, do it well. And I would say that it's been a very great pleasure talking to all of you. Long time since I came here and spoke. And I hope I've given you some idea about, the spirit of doing science. Whether it's crystal engineering, whether it's something else, it doesn't matter. Finally, the subject doesn't matter. Right now, I'm working on a project which you will all know about shortly, which is in some area which is completely outside chemistry. Because I always tell people that if you can do research in one area, you can do research on any other area. Research is only methodology. Methodology of doing research. When you finish your MSc, it's like you have got a passport. When you finish your PhD, you have got visa. It means your entry into the world of research, not into the world of chemistry or into the world of organic chemistry or into the world of making only 5-member ring compounds. No, means entry into the world of research. Research is research. So please enjoy, please do it properly. And all of you, God bless you. Okay, thank you.
For such a motivational talk, I think we are excited, and I think students are definitely excited. Well, if there's any questions. Well, I think we were journey as a scientist, developing a new field which was attracted international attention, and now everything is